a very active supporter of the Biopolymer Congress since ever, I would say. I'm delighted that he's about to take the stage, and thank you for your spontaneous jumping in, Patrick. For those who don't know Patrick yet, which is most probably a surprise, but nevertheless, let me bring a quote about himself, which we found on your profile on LinkedIn. Is I'm a passionate scientist and professor in the field of plastics processing. The focus of my work is on improving the sustainability of plastics products, in particular through the use of bio-based and biodegradable plastics. To do this, I use my deep insight knowledge of the formation of the microstructure depending on the process parameters. I get my motivation from the confidence of the sustainable plastics industry based on circular economy is possible. End of quote. So that's a great thing. So I'd like to feel your passion also in your speech. Thank you so much for jumping in. As said, let's welcome Patrick.
Thank you very much. Thank you very much. I hope I can fulfill these announcements here. And yes, I'm very passionate to tell you our latest results on PBS recycling. So my institute, or the institute I'm working in, is a material science institute. We are focusing on the microstructure of materials, because in our belief this is the key to customize the macroscopic properties. And we work a lot also with biopolymers in my group, and now I would like to show you what we found out. In the first part I would like to explain a bit why recycling of biopolymers is also very necessary, at least in Europe, and then show you the technologies needed for recycling, and then give you the main conclusions and take-home messages. Good. So, this is the scenario we all will face. There is no doubt. There is an increase in consumption of plastics in the next years, in the next decades, because there will be economic growth in many regions in the world. For example, in India, you can see India will be one of the main drivers of the economic growth in the world. And this means there will be consumption, and this means there will be production of goods, of plastic goods, which will be maybe used packaging as well. And other regions like Africa will also grow. And at the end, in this scenario from the OECD from last year, it turned out that we will produce every year 1 billion tons of plastics in the year 2050. 1 billion tons each year. And the question is now, and there we must all be realistic, can this amount of plastic be reduced from renewable resources? Today we learned that for PHA, the conversion rate is maybe 10:1, so you need 10 kilogram of feedstock to make 1 kilogram of plastic. It will be very challenging to do this, to find all the feedstock and to get all this bioeconomy processes into scale to do it. So, the solution, and this is the next scenario I want to show you, is recycling. So we need to recycle the carbon we put into the market. We need to recycle, we need to reuse, because if we do this, the amount of fresh material we must bring into the cycle gets less. And these colleagues from Nova Institute, they make a scenario where 20% of the carbon is coming from renewable resources in the future, and this is the carbon which must be brought into the system, into the cycle, to get leakages out, we all have, and so on. But the main of the carbon we all need for our plastics, for our biopolymers, must come from recycling. And we all know that there are many types of recycling today, and maybe in the future there will be other ones, but this is one of the key messages. Also, bioplastics must be recycled, just to keep the carbon in the loop, in the market we all need. We also learned today from other presentations that CO2 maybe is a good source for carbon and to make bioplastics in the future. Let's find out if this can be scaled up and so on. I'm very interested in this as well. Good. So this is the industry we must face, and there we have bio-based feedstock from different resources. And these feedstocks are then converted into bioplastics, and from these bioplastics we can make products. So we talk about different kinds of bioplastics, different kinds of biotechnology processes, different types of conversion routes. We learned a lot today already about these markets and these products and so on. So we can use this. This is already available. And I today would like to focus on a certain part of bioplastics which are bio-based and biodegradable, because they face a lot of increase in the market in the last years, and the increase is predicted to be sustainable, so there will be more increase in market share in the future. And here we think that especially the material PBS, so polybutylene succinate, is a material which is very interesting and can replace materials, petrochemical materials like PE and PP, so polyethylene and polypropylene, because the processing is quite comparable. Yeah, we learned a lot in the past that processing of PBS is possible for many different technologies, and the resulting properties of the products are also comparable, yeah, to polyethylene and polypropylene. So this makes this material quite interesting. And how is PBS produced? So you need a feedstock. This can be a direct sugar source or a second generation feedstock, so where you take out the sugar from lignocellulosic feedstocks, and then you have production of succinic acid and butanediol, and then the polycondensation to PBS. And in our view, this is just the start of the recycling again. Yeah? So we must keep this material, although it's biodegradable, in the loop. Yeah? We must recycle and keep the carbon in the market. Good. We showed in the past, as I said, that PBS can produce to many different products, especially packaging products like usually done films or blow molding, injection molding, and so on. So these are the products today made by polyethylene and polypropylene. And now, since we all, or at least I'm living in Europe, we must talk about regulations. So we know we can produce these products, we can make this packaging, but we have strong regulations on especially packaging and packaging waste, which are active and will be used in the different European countries from now on already. And those regulations are put in place to harmonize the national packaging production and recycling. And as you can see, for plastics, there must be today already, there must be 25%, next year 50%, and in the future 70% or even higher of the plastic, of the material brought into the market must be recycled. And this has different effects, because the producers will only bring material into the market which is approved to be recyclable. Yeah, because no producer will bring any material into the market which is not approved, because there will be no collection of these materials, or it will be used as for burning and incineration. And this is the strong reason why also, at least in Europe, bioplastics must be recyclable and must be approved as recyclable. Good. And when I say recycling, I mean in this field now mechanical recycling. There are other recycling routes like chemical recycling, or we learned about enzymatic, so biotechnological recycling. But mechanical recycling today is the working horse. Yeah, so this is an established system in Germany and Europe. So you can collect all the waste, and then you have different steps from this collection. You must start with sorting. So you must sort out the different plastics, polyethylene, polypropylene, polystyrene, or the other plastics. And in the future, also biopolymers like PBS or PLA. And then from this sorting step, you can start from grinding, milling, and then recompounding and reprocessing to new products. So, but the first thing is you must show that the sorting works. Yeah? So sorting must work in the existing equipment, in the existing collecting and sorting equipment, because these are facilities already active. And those facilities typically are now focusing on polyethylene, polypropylene, because these are the materials which are in the market, higher than 50%, so they fulfill their regulation. Yeah. So, and now the question is, can PBS, as a very interesting biopolymer, can it be brought into this recycling loop, and can it be sorted out, and so on? So here we looked together with our partner LLA Instruments into the sorting of packaging. And sorting today, industrial sorting is done by near-infrared technology. So you have infrared sensors, and those sensors detect what kind of plastic is on the conveyor belt, and then the sorting starts, where you then bring the different plastic products in the correct collection system, so that you have different branches of polyethylene, pure polypropylene, and so on. And infrared sorting means that you activate the product, the plastic, and detect the infrared radiation coming back, and then you get a spectra, and each polymer has a specific spectra, and then you can distinct between different plastics and sort them out. So, and here we worked with a test equipment where we can test this sorting mechanism and this detecting mechanism, which is comparable to the industrial sorting. So the test we have done, you can see here. So on the top, you see conventional packaging materials like polyethylene and polypropylene, and conventional products. And on the bottom, you see PBS products we made in our project. And the question was now, can the system, the infrared system, can it distinct between those products? And yes, we see that by near-infrared sorting, we see the difference of the conventional plastics and the PBS. So the green in the lower line are the PBS products, and you can see also what was detected are the etiquettes, which are still on top of the product. So, and now it's depending on the customer if this is a product which is approved as PBS, for example, and this is then the next step after the classification. You must do the object evaluation. So you must evaluate if this is a correct detachment, and after this you can decide, yes, this is a PBS product, and this can be sorted out into the PBS batch. So the first take-home message to say is, yes, PBS can be sorted. Can be sorted out in the conventional waste stream, and this is a very important point if you talk to all these collectors and sorting companies, because they need to know if this is possible with their conventional and active technology. So without further investment, we can say that, yes, PBS can be sorted out. Then the next question is, okay, so this is good news, but we maybe have different types of PBS or different types of biopolymers in the market and in the waste. Is it possible to separate also between them, so that maybe each producer gets his own PBS back and can recycle its own material? And here we found out that simple fillers like talc and kaolin, which are used in many different compounds already today and also can be used in bioplastic compounds, they also have a very specific spectrum in the near-infrared technology. And this you can see. So we see there at 1340 wavelengths, you see these specific bands, absorption bands of the fillers, and this can be then further increased, the contrast of this band in the first deviation of these lines. And there's a very sharp peak, and this can be used as a detachment. So talcum and kaolin work as a natural marker, or can be used as a natural marker in this sorting technologies. And this then we further investigated. So here you can see we made compounds with talc and kaolin of PBS with different contents. In the picture you can see on the top line the kaolin content is increasing, and downwards the talc content is increasing. And in the middle you have mixtures of talc and kaolin. So in total, you can make many different types of compounds, and you can detach many different types of materials at the end. This was clearly shown. Again, classification and then object evaluation. And in this example, yeah, we show that we can make 11, 12, or whatever, depending on the composition of the compound. You can make many different specific products which can be sorted out, and then each brand owner, for example, gets his own product back, yeah, and can recycle this material. This can be relevant for medical applications or specific food applications where really the brand owner needs his own material back. Good. So sorting, as I said, can be done also with bioplastics like PBS. And then the next question is, okay, I have sorted the material. You can see here different products we made in the project. On the upper left, there's a neat PBS fraction, which is maybe a separated fraction for medical applications, and the rest are mixed fractions for different compounds and different products. And then the next step is the cutting or milling of these materials and products to new flakes. So these flakes then can be used for recompounding and reprocessing. And here we worked also with an industrial mill. Yeah, the throughput was 800 kilos per hour. So these are the throughputs of industrial mills in this scale. And you can see also with different sieves, 8 millimeter and 6 millimeter sieve, we got this ground material with different sizes of the pellets. And there was no problem at all, even at this high throughput to grind and mill the PBS products. Even with a dry mill, so there was no water needed to cool down the mill and so on, which is also important information because PBS as a polyester is not very good to get in contact with water. You must do a lot of drying afterwards and so on. So this is not necessary here. So also the milling, the grounding of the material in the next step was no problem. And here we work together with Veolia. Good, and then the next step, once you have sorted out, you have collected, you have milled your material, you can start to do the reprocessing, the recompounding of the material. And here we worked in our own lab with a 25 millimeter twin screw extruder. And we did different recycling processing steps, so reprocessing steps of the material, up to 8 cycles. And in the first diagram, you can see the development of the torque of the twin screw extruder. So for the pure PBS, you see this slight increase in the torque. This is a known effect for a certain commercial product of PBS where there is a side branching during processing. And but the torque afterwards is quite stable. We additionally investigated 2 different PBS compounds, and there you can see, yes, reprocessing generates polymer degradation. Yeah, and so that the torque goes down, and at the same time, you can see that the flowability increased. So on the right diagram, the MFR or melt flow rate is shown. So with more recycling steps, you see that this value goes up, means viscosity goes down. And this is also a clear sign that a reduction in molecular weight happens during this recycling or reprocessing. Interestingly, we could not find any decrease in the mechanics, so stiffness and strength is more or less stable, but you see this decrease in molecular weight in the impact strength on the right diagram. A decrease in impact strength is also a clear sign that reduction in molecular weight happens during this reprocessing, and this of course is an information that you need always fresh material. Yeah, so to make new products out of completely recycled material will be very hard and very challenging. So you need modification or fresh material, and this 50% recycling criteria we must fulfill from next year on should be possible also with the PBS, at least for stiffness and strength. We also did not see any influence of the melt of the screw design. So we have investigated 2 different screws, conventional conveying screw and a certain mixing screw, and there was no significant effect of the screw design on the mechanical properties. Good. Also a very important question is the appearance of the material, so the coloring and so on. And here you can see that with increasing compounding cycles, there is also a change in the brightness and in the yellowness. So the brightness is the blue lines, means with the ongoing compounding cycles, the brightness goes down, so the material appears darker, and the yellowness goes up, so it gets darker and more yellow. And this you can see on the right side in the pictures. And we learned today in another lecture that there are modificators and additives which then should be used also to modify the material and to keep this problem under control. Good. So in our project, we also looked into the life cycle assessment. So is it really also beneficial in terms of carbon footprint to use recycled material? And here you can see that we have analyzed the complete value chain of the production of PBS. This would be the product level on top in the green box, and then you can separate these different processes into sub-processes, and those sub-processes again you can separate into specific processes. All of these different boxes have their own input and output, and at the end you can calculate the carbon footprint of your product. And what you can see is that for PBS, bio-based PBS, 60% of the carbon footprint is produced to make the polymer. Once you have the polymer in hand, 60% of this is the pure granule is coming, of the carbon footprint of this material is coming from the fermentation, the polymerization, and so on. And the rest then is produced through processing to a certain product for transportation and so on. So if you use recycled material, this 60%, of course, you do not have again in your material, and the more of the recycled material you put into your compound, of course, the least your carbon footprint. And here you can see some numbers. So 20% of recycling material, you get already a significant reduction, and if you use 50% or even more, you can see that also the carbon footprint of your material goes significantly down. Good. So to summarize and to give the conclusions and the take-home messages, yes, we think that PBS is a bio-based material which can be used to produce packaging. And yes, we show that PBS can be sorted out, can be separated from conventional plastics and conventional sorting technologies, and also can be granulated afterwards. PBS should be modified to stabilize it against this degradation effects we found in our processing experiments. And if you use more material, more recycled material in your compound, you can significantly improve your carbon footprint of your material. Good. I would like to thank the funding agency to give us the opportunity to do these investigations. And I would like to thank you for your attention. And I'm happy to get some questions to answer afterwards. Thank you very much.
Very good lecture, I like to say, and good to see that also biodegradable products survive in this tough environment in the European Union. By that, so I think that's a very good contribution. So
we do our best. Yes.
Yes, you did by that. So I think there are even further comments out of the auditorium.
Thanks very much for that. So my question would be: you mentioned that you need a certain percentage of PBS, fresh PBS, in order to keep up the product quality if you add recycled material. You said you can meet the 50% criteria, which will apply from next year on, I understand, but will go up to 70%. Mm-hmm. Will you be also able to meet the 70%, or is it time to rethink the EU directive in that way?
No, I saw, or I brought the scenario, if we get 20, if we can stabilize the material, that we only need 20% of fresh material, so that we have a recycling quote of 80%, then we would totally be fine in this moment. Of course, the more the better, but we see it from other materials that even 100% or plus 90% are possible. I mean, in the PET region, where we sort out correctly and have the material for a long time now under investigation, we have recycling quotes of plus 90% in some applications, like bottles and so on. So I'm optimistic that we can, at some point, we can also reach that with our materials.
Yeah, if I may, that was my question when I hit, that was very interesting. I thought if this EU directive giving a certain percentage of recycling percentage going up quite high, does that in the end mean that you favor the classical fossil materials and actually make it even more difficult for the biopolymers? Because
at this point, yes.
Okay.
Because it's very, it's okay. Let's assume the waste stream is 100% polyethylene. There is no problem to get 50% recycled. So there are many strategies now. One strategy is mono materials, so that we get rid of all these multi-packaging materials where different types of polymers are combined. So, and yes, one other strategy for now is to use polyolefins, polyethylene, polypropylene, and we must find our niche, with our biopolymers. And because I've shown also the LCA, for the LCA, for example, you need, or you use a renewable feedstock, so you get a better LCA. This could be an argument for these bio-based products in the market.
Okay, thank you.
So first of all, thank you very much for the very nice introduction, also to PBS. What is the reason? Do you know exactly the reason of the degradation of PBS in the recycling process? Because this is essential to improve the non-degradation.
Okay. Yeah, so we learned today already what are the degradation mechanisms. So you can have hydrolytic degradation, you can have thermo-oxidative degradation, I think those two.
But in your process, because you do the recycling process, so sure you can always say the normal ones, but it seems like that there's only one or two, maximum of two, specific problems in your, or challenges in your recycling process, and this you have to overcome. And then you have better recycling rates.
Yes, yeah. So we showed that mechanical properties, stiffness and strength is okay, impact strength is going down. This is a clear indication of molecular weight reduction. So this can have, I think, three different reasons. Cutting by the extruder, or hydrolysis, or thermo-oxidative degradation, and then you must stabilize. You cannot prevent all of these effects at the same time. And these are effects which are known from other polymers as well. So for me, this is not a bad sign. This is a normal sign. It would be a wonder if the PBS material behaves completely unnatural and there's no degradation at all by reprocessing.
Okay, thank you very much. Is there any possibility to make chemical recycling so that you, because you have a pure product, so to cut it down to the monomer and then you do...
Yes, so we learned also about enzymatic recycling. I think this is a very good option because chemical recycling is done at high temperature, high pressure and so on to crack the chains. If we use nature again, microbes and enzymes to break the chains at mild conditions, this would be, I guess, a much better idea, using less energy and also, again, producing less carbon footprint.
Maybe one last question, or one question from my side. What happens if you have PE inside, or PET?
Yes, so especially PE would be a problem. So PBS and PE or olefins are not a good idea, so they are not good compatible and you would get no good properties and there would be phase separation and everything. So PET as a other polyester could work out, but as I said, it's not the strategy to make mixture of different polymers. We must have a very pure sorting, and then we can get good products again into the market.
Okay, thank you very much.
Thank you very much, Patrick.
Okay, thank you.
Thank you very much.
lecture.
Patrick.